Wait 2 seconds. Where's my headphone? All right. And this, this. Hey. So GitHub is an exercise 6 today, right? Okay, we're gonna learn something fun today. Okay, please download exercise 6. Something fun today. Today we're gonna learn something that is like the direct opposite to what Ajahn cannot try to teach you. Wrong password. Why? Okay. Which one? Which one? This one? That one? This one? Okay, I think it's this one. Let me see which one we should start first. Let's do something boring first. Okay. Oh, let me remind you the midterm is next week. Let me remind you. Let's do the boring one. Okay. So reminder, midterm is next week. And why is my Zoom window? Didn't share the screen. Oh, God. Oh, I forgot to share the screen. That is why. And share window. Okay, now I share the screen. Should be good now. Okay, let me remind you, midterm is next week. It's gonna cover homework 1 to 4. Okay, so that means it's lecture 1 to 4. Okay, midterm is next week. Lecture 1 to 4. 1 to 4, and also means homework 1 to 4. Okay. Okay. I don't think I need to say this to you. Don't do something stupid. Don't do something stupid. It's open book, open notes, but what that means is that don't go online and ask people. Okay. So try to solve it yourself. That's what I asked you to do. Okay. Any questions so far though regarding everything? So that means you should do the homework. I see like a lot of people didn't do the homework. Do it, otherwise you're screwed. Didn't that happen in a class? No. We haven't get to a real lecture yet. We haven't get to the real lecture yet. Okay, I need my screen. I need my iPad, but I need to write something down first. 2 seconds. Okay, so the goal today is to figure out how to solve this. Yes, it's actually, we really don't like it. We try to give the freedom. We try to give the freedom to students. So those who are like doing normal thing that normal people do should benefit from it. Okay. How much time do we have for our exam? You have about a week. About a week. I'll post it at the early next week, and then you have about a week to do it. Maybe it's due on Sunday midnight or something. But it should only take you like 2 or 3 hours if you know what to do. It's not that hard. Midterm is next week, and any other question? So today is lecture 6. Any other question? Okay, let me go back to my screen. Today is actually a very easy lecture, but you're gonna learn something very important, that not all the problem can be solved with the magic algorithm like what Ajahn Kanat and Ajahn Sansan try to teach you. So then this is like learning how to brute force your way through ish. We're gonna learn how to brute force your way through in this lecture and maybe next lecture as well. Okay, not every problem can be solved using magic algorithm within big O and log n or something. Okay, most of the problem is much harder than that. Let me switch my screen. Switch. Wait. Oh, it doesn't have my iPad. 2 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Come, please. And let me make sure. Do not disturb. Okay, so the goal today, right? We learn how to solve equations, right? We learn how to solve like x equal to cosine of x. That we learn how to solve. We learn how to solve like 3x plus 5y equals 10 and 10x plus 2y is equal to 3 or something. We learn how to solve that, right? So this is called an equation. This is a nonlinear equation, right? This is called a system of linear equation. Okay, which we learn how to solve system of linear equation, right? You solve the matrix and so on. Right? This thing is easy. You do Gaussian elimination and so on. That thing is easy. You can do bisection or whatever you like. But what we want to do today is something a little bit different. Okay, we want to solve this, right? Which, if you think about it, is kind of mix up the two, right? It's nonlinear. There's an x squared over here, and it has more than one variable. So this thing is called system of nonlinear equation. You can try to solve this by hand. You might have some luck with it though. Okay, you might have some luck with it, but it's actually, you can see it's really hard, right? You may think, okay, Ajahn, I can do substitution. Yes, you can. Of course, you can try. You can try, and then you're going to give up on the algebra in a second. Okay? So the first thing that we can do is always to just visualize your problem, to try to understand what exactly are we trying to find. Okay? But before we do that, before we visualize, let's normalize it first. Let's normalize it. Okay? We want to normalize it. So essentially, we try to solve like fx equal to 10, right? And gx is equal to 57. So let's normalize every equation. So you can think about another system of equation. I claim the following, that you can write this in terms of the following: ux and y equal to 0 and vx and y equal to 0. Okay? So the thing on the top, we can write that easily, right? Just move 10 to the other side. So that means u of x and y is x squared plus xy minus 10 equal to 0. So that is u x of y, right? And v x and y. Sometimes when you write the code, you want to do this instead u of like the vector, and then you expand it inside. So you don't fix two dimension. Is y plus 3xy squared minus 57 equal to 0. Okay, so I claim that if we know how to solve the problem in this form, you can have as many variables as you like, but we're going to do only 2 because that way we can visualize it and see if we're doing the right thing. Okay, any questions so far though? I claim every system of nonlinear equation can be written as this. Okay, and if we know how to solve this, then we're good. Okay, so let me switch back to my screen. Actually, let me just copy it here. 2 seconds. Let me just copy it here. Oh, I cannot. Start recording. No. Yeah. Okay. So we just learned, right? We can write these two guys in terms of u and v. So let's just write that. Okay, I do this. So function u, which takes x and y, it returns x squared plus xy, oops, x times y minus 10. Return what? Y plus 3 times x times y squared minus 57. Right, and both of these are what we hope to find, that it has to be simultaneously 0. So let's visualize it. And as usual, this is u and this is v. These are pretty picture, but you can't really interpret anything quantitatively from it. You can see qualitatively, this is what it does, this looks like a saddle, and so on. So a better way to do it is with a contour plot. We learned that last time, right? Contour plot is the plot, right? It's the plot of the line of constant values, right? So for all the value on the green line, ux and y evaluate to 150, and on this blue line, it evaluate to 300. Okay, so far so good. So we can visualize u and v. Okay, so the question here that I have for you is, where is our solution though? Where is our solution, x and y? Where is it? Can you tell me? Where is our solution? Right. Remember that we want to find the place where x and y, somewhere near 0. But there's a whole bunch of line that it is 0 though. There's a whole bunch of line that it is 0, right? So for you, if you plug in any value on this red line, you're going to evaluate to 0. Right? If you plug in any value on this red line for v, v is going to evaluate to 0. So where is our solution though? Where is our solution? Anyone has a good idea? I want your intuition on this one. What exactly does it mean to solve it, right? We are interested in the point that satisfies the following, that u of x and y is equal to 0 and v of x and y is equal to 0. So where is it? Where is it on this graph? Can you tell me? Or tell me how to find it. Tell me how to find it on this graph. Okay. Yes, we can merge both graph, and then where's my solution though? I can merge both graph, right? So the blue are the V's, and the red are the U's. So where is my solution? At the point of intersection, but there are a whole bunch of intersection, right? There's this guy, that guy, that guy, and there's a whole bunch of intersection. Which intersection are you talking about, Sarah? Very good, right? Because we know everything on the line, right, gonna make u 0. Everything on the red line gonna make v 0. Everything on the blue line is gonna make u 0. So the point that makes both of them 0 are the intersection of blue and red line. Are we good? Right? So that means the point that we are interested in is exactly at the intersection, right? It has to be both 0. Someone good? This is a very important point. Okay, that you know how to visualize your problem. Otherwise, there's no way to check. Like, it's so hard to check if you do it right. Okay, so the thing is, so we would expect. So let's look at this one. There are two solutions. That is actually what you expect, right? For nonlinear, you don't have to expect that there's only one solution. Okay, you may have multiple solutions. So one of them is going to be around, I don't know, 4 and minus 2, right? So one of them is going to be 4 and minus 2, right? That's this point. If you look at the graph, and the other one is going to be x is about 2 and 4, right? What should I do? 2 and 4. So if you look at the graph, this is what you kind of expect. Okay. Any questions so far? Though? Any question? Now you know this is what we want to find. We really want to find that intersection. Okay, except that two variable, which we kind of not know how to do. We know how to do it in 1D. We know bisection. We know Newton's method, and there's a whole host of things that you can do. You can actually do bisection for two variable, but don't. Just don't. Just don't. There is a YouTube video on how to do it for two variables. So I might post it on Discord later. And then after you see it, you're gonna know why I do not teach it in the class because no one do it. Yes, you can sort of do bisection-ish algorithm in 2D. It's annoying. It has a whole bunch of details that you need to get it right. Okay, it's not like bisection you can write in 5 lines, right? After you understand, you can write in 5 lines. The other one gonna take you a lot more. Right, that's why you are learning computer science major, because you want to replace all the human, right? Humans should spend more time doing something more fun, like playing games and making games, right? Or for example, there are, like, you know, the drama with Chulalongkorn, right? That there are people who try to say preserve the tradition, right? But they forgot that their ancestors lived in a cave, and they didn't preserve the fact that they live in a cave for a good reason. Things change, so make sure you're ahead of the curve. Okay, now let's go back to here. So we want to solve it, and we want to solve it using Newton's method. But then you ask, Ajahn, Newton's method, you do all the intersection, right? That we did last time. But can we do that here though? Okay, that's the real question. Okay, let's do that together. Newton's method. Okay, Newton's method. We learned in 1D. Let me show you how we got Newton's method in 1D. Not geometrical though, because last time I showed you how we got Newton's method, right? We do this, we find the slope and so on, right? We have the curve, we find the slope. Oops, sorry, that doesn't intersect at 0. We find the slope here, and then we do here, and then we go up there, right? This is what we did last time, but in 1D. And I taught you in terms of geometrical meaning, but geometrical meaning will get you so far, but it gives you a very deep intuition on what's going on. And you're gonna believe that it works. But now we're gonna do something a little bit different. We're gonna reach Newton's method by another way. Okay. So here's how it go, right? Let's say we want to solve fx equal to 0, right? Which is like every single equation there are. Yeah, let's do 1D first, then you're gonna understand how to do 2D. In 1D, fx equal to 0. Here is the way that we're gonna do it. Okay, let's say you have some initial guess. You know that f of your guess, let's call that xn. Okay, f of xn, you know it's some value, not 0. Okay, not 0. And you know what we did so far is we learned how to improve our answer, right? Our goal is to improve our answer. So we hope the following going to happen, right? We want to know how much we should improve our answer, right? So it's going to be fxn plus delta x. Very good. So this is your improvement. Okay. Someone good? So if this is your improvement, what do you hope this term is equal to? What do you hope this term is equal to? If you make the right improvement, what do you hope it is equal to? What do you think? Right? Remember, our goal is to do this, is to find the value of x that you plug it in and the function itself evaluate to 0. Not minus xn, because you don't want the argument to be 0, but you want the return of the function to be 0. So what is this guy you hope is equal to? What do you think? If you make a perfect change, what's going to happen? It should be 0, right? Because that is what you hope, right? Because exactly that's the question, right? This is your new guess. Think about this. This is your new guess, right? If your new guess is 0, then that means you're good, right? Then your problem is really to find what is delta x. Are we good? So far so good? Your problem is really just to find delta x. Okay, so let's do this. Let's do this. Okay, f of xn plus delta x. Now, does this thing look so tempting for you to do something with it? Does this thing look so tempting for you to do something with it? Let's say if x delta xn, let's say if we're close to the solution already, right? If we are close to the solution already, delta x going to be very small, right? To make it equal to 0. So what is so tempting to do with this term? And make sure you know how to do this by like next week. What's so tempting to do? Anyone? Anyone? If delta x is small, what do you want to do? What can you do with it? This is a very important skill. Find the derivative? No, not find the derivative. What's so tempting to do when you see fx plus something small? What's so tempting to do? Also, we typically call it h, right? Get rid of something small. Get rid of something small. Yes, we want to get rid of something small. Okay, let me tell you what I want. When you see something like this, fx plus something, your first thought should be, if it's small, we can do Taylor series, right? That should be your first thought after this class. If you see the perturbation, right? Any kind of perturbation to the argument, we can do Taylor series. So yes, everyone up there is correct, except it's not the word that I want. So if I do Taylor series, what's the first term? Tell me, what's the first term? Delta x is small. F of xn. Very good. That's the first term, right? Plus what? What's the second term? What's the second term? Make sure you know this by like next week. This should be very good. Close enough. Okay, I'm gonna fix your answer. And then I'm pretty sure you know this, right? It's gonna be f double prime of xn. Oops, sorry, let me put n as well. And then over 2 delta x squared and so on. And it's an infinite series. Okay, is that one good? So this is a Taylor series, we know. So let me ask you, someone said the keyword. Justin, which term do you want to get rid of if delta x is small? Which one are you going to ignore? Which one are you going to ignore? Justin, which term are you going to ignore? It said get rid of something small. What is small here? What is small? The last one, right? So at least keep something with delta x. Otherwise, your function is going to be constant, right? At least keep something that has to do with delta x. Okay. So that thing is small. So we're going to say this thing is higher order term, which let me just erase it. Some people write like this, higher order term, which we're going to call that 0. Okay, we ignore it. We assume that delta x is small. Okay, and let me ask you again. What do you hope the whole thing is equal to? What do you hope this guy do? What do you hope it is equal to? It has to be equal to 0, right? Okay, which means if you look at this, you can solve for delta x, right? You can solve exactly for delta x. You know which guess is good, right? So that means from here, you can say that delta x is minus f xn over f prime xn. Okay, so far so good. That looks familiar, right? That looks familiar in Newton's method. That term looks familiar. So which means the following, which means your update rule, right? Your new guess is going to be xn plus delta x. So that means your update rule is going to be xn plus 1 is xn plus, actually minus f, actually let me play plus delta x, which is xn minus f of xn over f prime of xn. Okay, is that one good? Right? And we got exactly Newton's method, right? That we did last time. That's good. I am pretty sure. I haven't checked the history. I'm pretty sure when Newton's figured it out, Newton's method, he actually figured it out this way. Probably, most likely because he know what the derivative means. Okay. Any questions so far, though? Any questions so far? Make sure you kind of understand, right? We start with some guess that is not 0. Then we want to find the correction that we can add to it and gives them and makes the whole function 0. Right? And then we do Taylor series to make a good educated guess. That's going to be delta x. It's going to be some sort of linear function, right? You can solve for delta x. Actually, if you have higher order term, like if you add the quadratic term that we just erased, you can actually make a better guess, right? But there's a diminishing return. Yeah. This thing is actually fast enough. Newton's method is fast enough. Any questions so far, though? The next thing that we want to do is we want to extend this idea, the same idea, to higher dimension. Yeah. Anyone has a question? Anyone has a question? Okay. Any questions so far? Let's do multiple dimension. Okay, let's do multiple dimension. Okay, let's start with 2. Multiple means 2. If you know how to do 2, you know how to do like any number of dimension. So let's do 2. Okay, so you can start with the following, right? Remember, your goal is to solve this. Okay. You want to solve this. f of xn and y. Oh, sorry. You want to solve f of x and y equal to 0 and g of x and y equal to 0. You need two equations, right? Because you have two unknowns. You need two equations to solve for it. Okay? So let's start with this. Let's say you start with some guess, xn and yn. Okay? And then when you plug it in, you found that f of xn and yn is not quite 0. Okay? You also found that g of xn and yn is not quite 0. Okay? Right? We want to do exactly the same thing as last time. We want to know how much improvement we should make to x and y such that when you plug it in, it's better than 0. It's better than what we had before. Are we good? So the improvement is going to be delta x and delta y, right? If you know delta x and delta y, we know how we should improve our answer. So let's do this. Let me ask you the following. F of xn and plus delta x and yn plus delta y. What do you hope this guy is equal to? After you make the improvement, right? Xn going to be xn plus delta x and yn going to be yn plus delta x plus delta y. You hope that this guy is going to be 0, right? And you also hope that this guy is going to be 0. Okay, this is what you hope it does, right? A good improvement should do exactly this. Okay, a good improvement should do exactly this. Okay, so our goal is to do Taylor series and then figure out what is delta x and delta y. Okay. Okay. So help me with the Taylor series, multiple dimension. We did it once. I think we did it once, right? Last time we did it once. So what is it equal to? Taylor series. What's the first term? Tell me, what's the first term? At least you should know the first term. The first term. What do you think? Very good. First term should be just the function without the change, right? Okay. Plus what? Can you tell me the term that is linear with delta x? Plus what? What's the first term? If you only change delta x, how much would it change? If delta y is 0, how much would the function change? What would you do? Partial derivative of x, right? So it's going to be d by dx, which let me write this way. F comma x, this means d by dx of f. The comma x means partial derivative. Save my writing, that's all. Xn and yn and multiply by delta x, right? Plus the same thing for y, right? Times delta y plus some higher order term, which we're going to ignore, right? The next term is going to be delta x times delta y. If delta x and delta y are small, then delta x and delta y is like delta x squared, which is small. Okay, any questions so far? That we do the same thing for g, right? For g, that's the same thing, g of xn and yn plus, g of x, xn and yn times delta x, okay? Plus g of y, xn and yn times delta y plus the higher order term, which we're going to ignore it. Okay, which we are going to ignore. Any questions so far? Any questions so far? Okay. Let me rearrange things a little bit. Okay, let me rearrange things a little bit. With the help of technology, I can do this. Copy and paste. Let me rearrange things a little bit. Remember that this guy should be equal to 0, right? Let me get rid of this as well. Both of these need to be equal to 0, right? And what I'm gonna do, I'm gonna move this F and this G to the other side. Okay. So that means what's gonna be left with is minus F of xn and yn, right? And this thing is going to be minus g of xn and yn, which looks scary, right? But let me emphasize you. This is a number. This is a number like 5 and 3, right? This guy is also a number, right? All the partial derivative. These are also a number. It looks scary, but it is a number that you evaluated beforehand. Okay. So can you tell me what should we do next? What should we do next after we know this? What should we do next? Find delta x and delta y. Yes, you use linear algebra because this now is linear. Okay, right? This is actually goal in life, right? If you have a complicated problem, if you can turn it into a linear problem, then you have a whole bunch of tools in the back to solve it, right? And this is why we do Newton's method, because it turns nonlinear problem into linear problem, because we ignore all the nonlinear terms by definition, right? Because we ignore all these, we turn nonlinear problem into linear problem. Then we can do this. So let me write this, that it looks more like a linear algebra problem. Okay, let's try it as a matrix, right? Which we learned already how to solve it, like, but you're not gonna do it with your library though. Just use np.linearalgebra.solve, even though you wrote it yourself. Right? So this would be f of x, xn and yn, f of y, xn and yn, right? And then g of x, xn and yn, g of y, xn and yn. Okay, and that thing has to be equal to, do not screw up the minus sign. I did screw up the minus sign so many times in lecture, and it takes me a while to figure out where is it. G of xn and yn, right? Which means you can throw it into a Python and then it's gonna solve linear algebra for you, right? At the end, you're gonna get delta x equal to some number, delta y is equal to some number. And then what you can do is that your next guess, right, xn plus 1 is going to be xn plus delta x, and yn plus 1 is yn plus delta y. And equipped with this, now you kind of know how to do like higher dimension, right? You can actually guess what the matrix looks like. Okay. This is actually how the, what's that called? How the thing that we used last time, the scipy.optimize is implemented with Newton's method with the gradient descent. Okay. Any other question though? Any other question? Any question? Okay. This technique is so powerful. It's the basis of like everything. This technique is so powerful that you can linearize the problem and get to a linear problem and then solve it with linear method. Okay. A lot of problems in real life, especially in engineering and whatnot, are non-linear by nature. If you can linearize it, then you're good. But in my experience, you need to convince the client that linear is good enough for our purpose. Okay. Any other question though for this method? Because you need to implement it. It's going to take you like maybe 10 lines, 20 lines at most. Most of it is figuring out how to do partial derivative. Okay. So if there's no question, this is what I want you to do. This is what I want you to do. Let's go back to full screen. I want you to do I want you to essentially just find a solution for these two. Just find a solution for these two. Okay. Just find me the solution for these two. Where exactly it is. So I want self start with x and let's fix it to two variable, doesn't matter. So this is gonna be initial point and give me the solution. Okay. So please do this. Just give me x and y. Let's do it. And if you got the answers, let me know. Let me help you with the partial derivative. Okay. Let me actually write something that doesn't look like your code. Wait, is it wrap or wraps? At least you learned some funny Python tricks today. Okay. It works. Yay. Okay, this function should make your life a lot easier. The thing is, okay, any questions? This should make your code over here a much better one. Can we use the definition of partial diff? What do you mean? What do you mean by using the definition? The definition is exactly this. It's exactly this. You learn how to differentiate, right? You keep everything else fixed except you change only the argument that you want, right, Thanawin? This is exactly the definition. This thing is actually optional, but whatever. It's gonna complain if I do this. What is star arc? Good question. Is the following. So for example, let me give you some Python lesson. Star arg is called, I don't know what it's called. The official name is called variadic. Variadic argument. It means argument of any number. So for example, if I do this, and then I'm gonna print R, and then you can call R or I don't know, 1, 2, 3, 4, 5, 6, 7. This is not passing a list though. Look at this. I'm not passing a list. I'm passing a positional argument, right? So the ARG is going to be that tuple of every argument packed together as a tuple, right? There is also another one called called data KWD, and then you can print, right? So these are the keyword argument if you have the double star. This is a very nice feature of Python language. This way, you can actually write a program that writes a program like this one. Write a program that write a program. But don't overuse it though. It's so hard to read. Don't overuse it. Use it only when you need to. Yes. Use it only when you need to. Don't use it like don't use it like too much. Use it only when you need to. But these two are pretty common, especially if you look at matplotlib code. Oh, the KWD are the one that has a keyword. The ARG is the one without the keyword. Right, so I think you have seen this one before. You have seen this one before where you do like dict of A equals to B and C equal to D, and then it returns you the magic dictionary, right? The order doesn't matter, it's a dictionary. Oh, actually it does because dictionary in Python is actually an order dict. So So if you switch, so for example, if I put X over here, it's gonna put X in the back. So dictionary in Python is not like dict in Java, is an order dict, which means it knows which the order of insertion. So, but you should not make it matter, but it's actually matter in Python. They keep the order, but you should not rely on that order as a good practice. It doesn't work though. It's a wrong Python syntax, right? So it's a positional argument follow keyword argument doesn't work. It's a Python syntax problem. Okay, but I give you this to make your life a lot easier. You can generate a partial derivative function from any function you like. Okay, at least you learned this today. At least you learned this today. Okay, which should make your code a lot easier to read. So that means we just need to build a matrix, right? Matrix A is going to be actually let me write it like normal people would. Let me not do it. Let me not do something too fancy. So it's easier to read. Why is some people call the style of writing that kind of code meta programming, which is like getting a program to write a program, but whatever you call it, doesn't matter. So this is X, Y, X and Y. Why are all my plugs in? Okay. You can actually make this work for infinite number of dimension, but I'm too lazy today. You get the idea. Okay. I can actually save some line. Yeah. I call it U1B, right? I guess it to be 412. Review error 1. Okay. It gives me 2 and 3. Okay, close enough to 0 in my book. as well. Name it better. Yeah, you get this exactly. The other one, let's start at -5. Where does U and V come from? Very up top, very up top, over here. You move 10 to the other side, move 57 to the other side. Let me just copy U and V down for you. Let me put the code so you can compare. The only way that you will understand this class is to actually implement it yourself. Otherwise, I know it's very easy to copy and paste my solution, but like I said, I'm not trying to hurt good people. I'm trying to promote good people. They have something to check against. I can do this and then I can start again. X 10 and Y is -5. There, I got two solutions already. If you're done, raise your hand though. If you're done, raise your hand because I have something more fun to teach next. Like I said, this thing is the boring part of today. The fun part is next. How to spell linear not algebra. So it's ALG. Yes, linear not ALG. Wait, did I screw up the get left? I pushed a new one, it should work. Oh, now I push a new one again. Is if you're done, raise your hand so I know that you're done. Oh, I can do this. I give you until 1:45, and then we're gonna do the next thing. Okay, the code is push. Try to do it yourself. You can see it's not that hard, like 25 lines with the magic function. Okay, I give you until 45 to write this. Be right back. Okay, at least one person done. Okay, so for those of you who are done, if you remember last time what I said, right? I said that every problem is an optimization problem. So what I'm gonna ask you is, can you write this as an optimization problem? Right? And try to write it and then try to do gradient descent. You should end up exactly what we found, something close. You're gonna end up with something really close to what we found. Okay, so let's go to the next one. This is the next thing that I want to teach you, which is all your gacha game is based on this exact thing called pseudo random number generator. Okay, so let me ask you, let me ask you, did you have any idea though when you play gacha game, right? How is your random number generated? What do you think? What do you think? How does it do that? Right? A number between 0 and 1. How do you get a number between 0 and 1, right? How do you get a number between 0 and 1? I don't know, right? So let me show you. Let me show you. There is, but np.random. So think about this. All you get computer to do, right? What you learn in Python, every operation is deterministic, right? But But if you want something random, where do you get that randomness? Right? Random number for sale. Wait. Where is this? A lot of guys, random number. Where is this? I don't know. But there was actually a service. There was actually a service where people do this. Let me show you. So you can buy random number online. You can essentially buy random number online. So you have to send in a mail order, and then there's a girl in some house that's gonna roll the dice for you and write the number and send the mail back to you. That's a random number service. Which that idea is actually not that bad if you know something about blockchain. Okay, in blockchain, if you learn if you learn about blockchain, I think it's going to be open maybe next term or next term. We're going to invite someone to teach about that. One of the problem about the blockchain is that you're going to distribute your program to multiple computers, right? And you need to make sure that everyone return the same thing, right? So if you get random number for everyone, you sort of screw. And you don't want people to know ahead of time what's the random number gonna generate. Like think about lottery, right? If you know what's the lottery is gonna come out next, then we're good. So there's a service called Random Oracle. Random Oracle blockchain. There's actually a company in Thailand. If you know Band Protocol, they actually give this service. Uh, chain link, random number. If you know this company, they provide random number on the blockchain that you can use. That's all. And they generate like a whole bunch of money, right? So when Tan Tong said it's the best business idea, someone actually do it. There are a couple companies in the blockchain world. It's called Oracle. There's a Chainlink, and there's another guy called Band Protocol, SCB company. This the owner is a mathematics Olympiad, about 5 to 10 years younger than me. So this is actually the first Thailand unicorn, but they are not actually startup. They make tons of money. So the idea of having a girl throw a dice to you and mail in the order, that's actually not not a bad idea. They do some other service as well, but this is one of the service they provide. Okay, but that still doesn't answer the question, right? How is the random number get generated? You will feel disappointed if I tell you that the random number you get is not really random. It's actually deterministic. You would feel sad, right? But that actually what it is. So let me show you. Linear congruent. This is actually the way. No, there's no one rolling the dice here. Uh, the easiest way, okay, is something called linear congruent. Let's try it ourselves. So let's try the random function ourselves. LCG. Okay. And then yes, let me you actually if you want it proper, you need to write a class, but we're too lazy today. So x equal to 3. And so there is A, B, and K. So here's what it does. It say that the next number actually just write class. I think that's better. Class LCG. Actually, let's make it better. Let's make it data class. Oh, sorry. LCG for linear congruent method. A is an int, b is an int, and k is an int, and x0, let's say x is an int equal to 0. Okay, there's only one function. We say that x and the whole thing modulo k. So you can see there's only one line. You can actually write in one line if you use for while operator. Return x. That's it. So we can do LCG and then A and B, which is 100, 100. And let's put in all the prime number. You need something with it has to do with co-prime number. And then I can do for I in range 100 print dot next. What next text? Oh, I forgot self. A is not defined because it needs to be self dot A. Okay, that probably looks random to you, right? This is actually like everything. This is how you get the random number. Okay, so this is called linear congruent method. That's it. It say that the next number is the old number. You multiply by some number and xn and then plus b and then modulo with k. That's how you get a random number. This simple thing is actually what you get. So if you Google linear congruent generator, you're gonna see a list of, so there, this is the list of number that they use for A, B, and K. They call it A, C, and K. So for example, for Python, it's actually libc, I think. There, for Python, they do this. Okay. So multiplier, increment, and modulus. Okay, so far so good. So let me show you one problem with it. Let's try with something small. Let's try to show you 2, 3, and then let's modulo 11. What do you notice though? What do you notice? Okay, these three number is not exactly random though. You need something about the fact that it being a co-prime number. There is a pattern, right? You can see that 10 appears like regularly. Why do you think that is though? Why do you think that is? Why do you think that happens? Why do you think that happens? Not limited number of primes. Modulo? Well, modulo can kind of give you what's it called? Kind of give you 10 number, right? It's guaranteed. If you modulo by 11, it gives you actually 11 numbers. But then, but then think about this. Even with 10 number, you should sometimes see like three next to each other, right? Right? You should, if you generate enough random number, you should sometimes see three next to each other, but you never see it here. Why do you think that is? Like you never seen two things next to each other. 10 somehow spaced out in a regular interval. From the expression here, can you tell me why that is? What happens? Okay, so this is actually the problem with this kind of method is that it is deterministic. So think about this. The next number is fully determined, right? It's fully determined by the last number alone, right? So that means if you start with 4, the next number is going to be 1, right? So if you get to 4, the next number is going to be 1. So that means you're going to get a cycle length, right? There is a cycle length. And that cycle length comes from the fact that you only have 10 numbers, right? And then by pigeonhole, then the length has to be at most 11. The length has to be at most 11, right? Because if you end up with the same number, you're going to generate the same sequence over and over. And this is called the cycle length. Okay. With this method, there's a problem of cycle length, which the size is about k, the modulo itself at the end. Okay. So the easiest way to fix, which doesn't really fix, it's more a workaround. Easiest workaround is to like make k really large. Really large. Not a fix though. Okay, make k really large, then your cycle length gonna be much larger. Okay, so far so good. Or you can notice that k is really large, like 2 to the 32. This is 2 billion. Okay, for more modern language, you probably use 64-bit. Okay, more for modern language, use 64 bits. Okay, or this is not on the scope of this course though. If you want to look at, if you want a really long cycle length, there's a way. It's called Mersenne twister. This is not Mersenne. How do I spell it? It has to do with a whole bunch of prime property, which I never got it. But if you want a real random, a better random number generator, do Mersenne twister. I don't know. It has to do with a whole bunch of prime number and factorization, which I have no idea what it does. Mersenne and N, right? Thank you. It's called Mersenne twister. This is a much better random number generator. So this thing, when k, that means k is around 2 to the 32, which is 2 billion, right? I think this guy is 2 to the 96 or something, which is like, forget it. Right? The cycle length is 2 to the 96. This thing is 2 to the 32. 2 billion, you can reach it though. Like think about Google, right? You get search number every day, right? 2 billion, you're gonna hit it in no time. Okay. Any questions so far though? Like we have the cycle length, right? The easiest way we're gonna work around with, we're gonna make that k modulo really big, and then we have no problem. Okay. So then, if you look at my homework or my code a little bit, you're gonna see this line. You're gonna see this line, right? np.random.seed, right? And then I put number like 555 in or something. Okay, that seed is actually x0, the first thing that you put in. They do some manipulation with your seed, but for this method, to get the next number, you need the previous number, which you don't have, then you make the seed. Okay. Okay. So that's good, right? Now you know that if you give it the seed, all the next random number generator is fixed. So it's not random anymore, right? It's not really random in your sense that your gacha god is not random. Okay, anyone has a question so far though? Anyone has a question so far? Okay, so that is how you generate integers. Okay, which, you know, if you generate like 32 bits integers, right? How to scam gacha? If you know the seed, you know the future. You go figure out what the seed is, then you know the future. If you know the seed, you know all the future. Okay, that means they probably keep the seed secret. They probably use Mersenne twister though, so it's like almost impossible. Actually, you can do data mining on this to figure out what is the seed. If you know A and B, right? If you know A and B is like public. A and B is public. You can look at this table. These are A and B's, right? A and B are public. You can do data mining, right? You need at most like how many numbers? I think you need like 10 or 20 numbers to figure out the seed. Okay, so let's do this. Is Gacha at 0 and no. This thing has no concept of time. So some people do the following. Some people read, they say the temperature of your CPU as your seed to make it random enough. But if you think about it, CPU gonna run at like certain range of number, right? Or some people do like counting the network, the incoming network traffic, right? Like how many bytes we got already, and then modulo that by something. Okay, so sometime when you probably never seen this, sometime your computer gonna complain not enough entropy to generate random number. This is what it means. Just let it run for a while. It's gonna figure out how to generate random number. Okay. Okay. So, but what I want you to do, right? What I want you to do is to make sure the following, right? Typically, in numerical library, you are given one random number generator, which is okay. Oops. Import NP, numpy SNP. You're typically given one random generator. Okay, you are typically given random number generator, which give you some random number between 0 and 1, right? Okay, so your goal, but sometimes you want something else. Okay, sometimes it even have rand int, right? Even have rand int, you can tell it from 1 to 5, right? Yeah, it even have rand int. So numpy.random gives you uniform random number between 0 and 1. Okay, so rand int give you integer and rand n give you a Gaussian. So let me show you. Xs is np.random rand n, and for x in range, let's say 1,000, and then we can plot the histogram. We can plot the histogram, which looks normal enough to me. Right, it looks normal enough. Okay, but all these are like fixed number between 0 and 1 and between 0 and 1 and so on. So let me ask you, what if I want random number float, not int, from 0 to 5, what do you do? What do you do? You have a function that generates random number from 0 to 1, but now you want 0 to 5, what do you do? Can someone tell me? Just multiply by 5, right? So for example, we can do xs np.random or x in range 100, right? So this thing gives you 0 and 1. So if you want 0 to 5, you just multiply by 5. Yeah. prt.yes xs. This is the trick. If I put semicolon, then it let me make it like a lot more because I make a whole bunch of bins. Okay, so you get a random number between 0 and 5, which is fairly uniform as well. So far so good. So this is how you get 0 to 5, right? What if I want it -1 to 1? What do you think? What if I want minus 1 to 1? Anyone has a good idea? What if I want minus 1 to 1? I cannot just multiply by minus 1, right? It doesn't work. It doesn't work. What do you think? What should I do? What should I do? You cannot just multiply by minus 1 and hope that it works. Can anyone tell me? Do something like clever. This is actually a standard trick, but if you figure it out yourself, you're gonna remember for the rest of your life. Do twice for minus 1 and 1, then add. Not a bad idea, but let me show you what you're gonna get. You said that you get this, right? And then you add this, right? Let's see the nice picture that you have. Not uniform, right? Not uniform. But the range is correct though, Saran. But the range is correct. You can actually compute this. You can actually compute this. It should be a triangle. This is already correct. If Saran, you wait for like 2 or 3 weeks, then you learn about probability distribution. You expect the triangle, yes. Because to get this, there's only one way for you to get this, right? To get one, is that the first one return 1 and the second guy return 0. But there's a whole bunch of ways you can get 0, right? Minus 5 and 5, minus 3 and 3, and so on. There's a whole bunch of ways you can get 0. So 0 is the highest and that is lowest. But I want uniform. I want uniform. Anyone has a good idea? Do something that sounds so stupid, but so clever. Anyone? And subtract by 1. Okay, let me tell you the easiest way. Just multiply by 2 and minus 1, right? You multiply by 2 to get the right range first. Multiply by 2. So when you multiply by 2, it becomes from 0 to 2, but then you shift everything back by 1. So minus 1. So that's what you get. So not only that you can multiply, you can subtract as well. Are we good? Right? Now, how about this? How about this? Let's start with this guy. Ran n. This is actually in most of the standard library. Oops, sorry. Most of the standard library that it gives you a Gaussian random number. I think in the homework you're gonna need to generate some funny distribution. Okay, so any good idea? Any good idea? If so, you can see that this guy is mean 0, right, and width of 1, right? Mean 0 and width of 1. If you take statistics before, what if I want the mean of 5? What do you do? And width of 1. What do I do? I want to move this guy to the right by 5. What do I do? Multiply plus 5, right? You just put plus 5. And now the mean is going to be 5. Let me do it on it again. Okay, that looks better, right? Just plus 5 and then mean going to shift to 5. And the width is 1 again, right? It's from 4 to 6. What if I want something more narrow? Well, what if I want the width to be 10? Anyone has a good idea? What if I want the width to be 10 and the mean at 2? What do I do? What do I do with this? To get the mean to be 2 and standard deviation of 10. Anyone has a good idea? What did you learn in discrete math? For those of you who took it already. Okay, let me show you something funny. So if I multiply this guy by 3, let's see what happens. Then the width is now 3, right? The width is 3-ish. Right, so you can change the width by multiplying by whatever number. So if you want the width to be 10, you multiply by 10 and plus 2 if you want the mean to be 2. Are we good? Right, that's what you do. So you can manipulate this to any kind of distribution that you like. Okay, I think in the homework you're gonna get to, if you try to generate something that looks exponential, there's a way to. If you want exponential distribution. Okay, so far so good. So let's get to the use of random number generator. Okay, the first use that you're gonna see is how to do this integral. Okay, you can see that this integral, for those of you who take Cal 3 already, right? You integrate it 3 times for each variable. This is the volume integral. Okay, so you can see even the symbol looks scary. The real computation is even more tedious than if you try to do it. The real integral is even more tedious. Okay. So for a second, we're gonna use Monte Carlo. We're gonna use random number generator to do it. But first, let's do something simple. Let's do something simple. Let's do something simple. Okay. So let me change my thing. Let me change my screen. Let's go back to my iPad. Okay. Let me go back to my iPad. So let's look at this game. Let's look at this game. So let's say it's the box of the size of 2 by 2 by 2. Okay, 2 by 2. This is a square of 2 by 2. And then if I have a circle inside, okay, if I have a circle inside, okay, and then I want to figure out the area of a circle. Of course, you learn that it's pi r square, but let's forget the fact that we know pi r square. Okay, we know how to find the area of a square. That's clear, right? That's a 2. Okay. Okay. So, so here's what we're gonna do. Here's what we're gonna do. This is actually the correct the way they compute pi. Wait. But this is one way to do it. Okay, the way we compute pi. So let's think about this. If I randomly, uniformly pick a point within this range, within this box, right? So you pick a point within this box, randomly and uniformly, right? Sometimes it's going to be inside the box, sometimes it's going to be outside the box, right? So how would you find the area of a circle then, if you know that the total area is 4? What do you think? How would you find the area of a circle? Given that we did this so many times, we figure out how much of them lies in the box, and how much of them do not lies in the box, and so on. What do you think? What do you think? Right? So easiest way, think about this. You have your intuition somehow that the number inside circle, okay, right? It is going to be the total number multiplied by the ratio of the two area, right? A circle over a square, right? If you generate, I don't know, 10,000 points, some of them are going to lie inside a circle, right? Then you can figure out the area of the circle by just the number of the thing inside over the number of thing total multiplied by the area of the square. Then you're going to get the area of the circle. So Pascal, which you know it has to, it is pi r square, which is pi, right? We can do exactly the, let's do that real quick. Let's do that real quick. Okay, everyone understand the idea, right? This is the idea that we're going to use to find the integral, but let's do the easy example first. Okay, the easy example is this one. Okay, so let's do this. Let me add another cell. Let's find the value for pi. Brute force. Like this is the stupid thing. Okay, so you need to generate a point, right? So you need to generate a point. So that means let me write a really bad code. Generate a point, right? Then return entry.random, right? But we want to generate it from I don't know, -1 to 1. So that's multiplied by 2 -1. Okay. And so this gives you a point in -1 to 1 and -1 to 1. Okay. The idea, right? And then for points, this is not the best code, but you get the idea. Get 10 point for I in range 300, 3000. Wait 2 seconds. I think I need to skip something. Okay, we might need to skip the last one. We're gonna do the next. Okay, for point in. So we need to count the number in, right? So inside is 0, outside is 0. So if for point includes x and y is point, if x, so to check thing inside the circle, you just do this like x squared plus y squared is less than 1, right? It's like inside the circle, center at 0, radius 1. Then inside plus equal 0 plus equal 1, right? Print inside equals, let me just photo over here. Over total. That doesn't look like a pi. It's a pi of 4. What did they do wrong? Oh, I forgot to multiply that by the area. Multiply by the area, which is 4. Okay, close enough. Let's make the total like crazy. Yeah. Everyone got the idea, right? The idea is simple. So you can make it even worse. Don't do this on your computer though. It's gonna take a while. Okay. At least you get the 2 digits, right? At least you get the 2 digits. Okay. Any questions so far though? Any questions so far? Okay. So this is something along the line of running a simulation. Okay. Which we probably gonna get to do next time. This is along the same line of doing the simulation. Okay. Any questions so far though? Any questions so far? You guys are really quiet. This thing is simple, right? You generate a whole bunch of points. If it's inside, you add one. If it's outside, then you don't add one. Okay. What's outside for? Nothing. You don't really need it. You don't really need it. Okay. So let's try to do our thing. Okay. Let me try to connect you with everything. Okay. So what we did over here, when we find pi, I claim that you actually find the integral. Okay, you actually find the integral. This is the function that you're looking for, right? When you did it, you did the following. You do double integral, right? Over a 2x2 box, right? Multiply by the function times the area, dx, dy. Okay? Okay. This is what you're doing. But let me make it a little bit more concrete because this thing looks a little bit more complicated. But let's think about how we would do multiple integral. Let's look at two dimensions. Okay. Let's look at this thing is a box of size 2x2. Okay. And then I want to integrate, do the double integral over the box of 2x2 of some function, let's say f of x and y multiplied by the area. Right? So physically, when you think about double integral, right, you should think about it as the sum. Okay, you should think about it as the sum. So the function f has the value everywhere, right? The easiest thing for you to do is to do the grid, right? If you try to do this, think about this. This is exactly what you did with trapezoid, right? You make the function into a whole bunch of grid that you know how to find the area and so on. This is the same idea, okay? So this is the sum over all the areas, right? All the little areas of the function itself of x and y of that area of that box, right? So for example, if when you sum to here, you add the value of the function, typically in the center, right? Typically in the center, and multiply that by the area of this thing. This is exactly the definition, right, of integral, right? You sum the function over all the areas, okay? And this guy multiplied by the area of the thing. Okay, so let's think about this. Let me claim that this is a terrible idea to do. You could do it. You can write the sum this way. I actually write a library that I need to do this sum because I cannot get away otherwise. Okay, so let's think about the number of terms in the sum. Okay, if there are n blocks over here, what is how many blocks do you need to add up? That sum over there. How many blocks do you need to add up? Gonna be n squared. But what if you do triple integral? Gonna be n cubed, right? And then if there are like d dimension, then it's gonna go to n to the d, right? This thing grow exponentially with the number of dimension, right? So this is a terrible idea that you just can't do it, right? You just can't do it because this thing grows exponentially. Okay, so when what you did with Ajahn Kanat, right? When you see n square, Ajahn Kanat start complaining. N cube, then you turn off your computer. If it's exponential, then you take another course with Ajahn Sansan on how to deal with NP problem. Okay, so you don't want to do it. Okay, so you don't want to do it. This has an official name. It's called the curse of dimensionality. If you want to sound smart in an interview, say this word, curse of dimensionality. It just means that the number of things that you need to do, that the complexity goes like n to the d. Goes like something, some number to the number of dimension. Okay, that d is bad. Okay, so now let's compromise. Let's do some compromise. You say, okay, Ajahn, I know that if I try to add up all n to the d, right, I'm gonna get into troubles because there are too many grids. Okay, now you are now very lazy. You're gonna do the following. Ajahn, what if I randomly pick what to add? So that means, so for example, in this n square, you may only pick this. No, you may only pick these people. Okay. You may only pick these people and you say, okay, somehow I am going to use the sum, right, to represent the whole integral. Okay. So that's good. So that's good, right? Okay. So for example, that thing, so instead of summing over all the blocks, right? So let me write this, all the blocks. I am going to change it to sum randomly picked box. Randomly picked box. Okay. And let's say there are n of them. Some, let me use some other, let me say there are m of them. So we're not going to add over all the box. We're going to add certain number of box and maybe we can say that it is sort of an integral. Okay, so the value of the function doesn't change, right? Because the value of the function is whatever box you pick, right? It's going to be whatever box you pick over here. The value of the function is changed. But now, how about the area of the box? Okay. Okay. So let's say that the area here is A, the total area is A. If you pick only 10, if you pick only 10 points, what's the best thing that you can do about to tell what is the representative area of what you picked? Right? Good. So instead of using the area of that thing, right, you're gonna say, okay, Ajahn, maybe I'm gonna do this. So that's good, right? So if we pick M box, okay, maybe I'm not gonna tell you that it's exactly that area. I'm gonna expand it, right? So if you just want to make sure that the total area adds up to the correct thing. So you say, okay, on average, this is the area that it takes. And this is what we're gonna do. This is the Monte Carlo integral. What we just figured out, this is the Monte Carlo integral. The idea is very simple. You don't want to use every single grid because if you use every single grid, it's gonna take forever, right? It's gonna take forever. What if we only pick some grid, right? And then we're gonna say that okay, each of the box that we pick, the area are going to be like the average of the total area. Okay, so this is what you do, right? This is the total the whole idea, which sound very magnai. I'm not sure what magnai is in English. Anyone knows what is magnai in English? It means it sounds so stupid, too stupid to be true or something. Okay. So the way that we do this, right? We're gonna do this. That means all you need to do is to generate a point. The points. Okay. Evaluate the function, right? Evaluate the function. Right? Evaluate the function. And then sum it up and then multiply by A. Divide by M and then do it done. Divide by M. And then you're done. As simple as that, right? Okay, so far so good. So that means, let me do this. Integral of f of x, y, dx, dy. This is essentially the area, dA, of something in the range, right? When we pick box in the domain. Let me put the domain. So this is the domain. The range that you try to integrate over is equal to this. So let's write exactly this. Okay. And then we're gonna do some analysis. You may ask, Ajahn, you are not doing anything better. Yes, yes. Actually, you're doing something a lot better than last time. This thing is exponential. This thing sounds even more stupid than this guy, right? So the proper one sound really smart, but this one sound really stupid. But when you do stupid things, sometimes magic things happens. Okay, so let's try exactly this, and then we're gonna do some analysis on this algorithm on like how fast conversion, everything. Okay, let me change to full screen and okay. So for this one, it's very easy, right? It's you just generate a point in a queue. So let's do generate a point, right? You know how to generate this. You just do this 3 times. You just do this 3 times. Okay. Now you are sure that whenever you generate, it's going to be within that box, right? Now you need the sum is 0 for points. Okay, let me just do this for I in range. Let me make M is 100 range of M. Oops. Let me define F over here. Define F. And then it's X, Y, and Z. And it is going to be X squared multiplied by Y minus 1, and then square multiplied by C minus 2, and then square multiplied by exponential X times Y times C. And then return. Okay. And then S plus equal to F, X, Y, and Z. And then I just need to print, right? S divided by M and multiplied by the area, which is 8. Okay, that's going to be this integral. You can put it in Wolfram alpha if you like. Okay. You can put this thing in Wolfram alpha. I think you can do. Let me just do just that. Okay. This thing is easy enough to put in Wolfram alpha. Integrate x squared times y minus 1 square times c minus 2 square multiplied by exponential of x times y times c. I think it needs this guy to be capital E. Dx. And x is minus 1. Y is 1. C is minus 1. I think this works. Okay, that works. Oops, it doesn't like me. Close enough, right? Oops. Okay, so far so good. So you can see even this simple integration, right? Standard computation time exceed because of that curse of dimensionality. This thing is probably some Monte Carlo as well. Okay, any questions so far though? Any questions so far? But you can see the bad thing about this is that every time you run, right? Every time you run, you're gonna get a different answer. So if you want a fixed answer, np.random.c. Good question, Saran. Which we're gonna show, which we're gonna talk about that right next to this. Okay. So you can see the problem here is that every time you run, if you don't have the seed, right, it depends on your luck, right? It depends on like which point that you pick, which box that you pick when you do the integral. You're gonna get different answer. Okay, so far so good. So here's going to be the thing that happens. We're going to try to understand this, the behavior of, of what we get. So let me show you the following. Okay, so the behavior is the following, right? You know that if you run it next time, you're not going to get the same number. That means if you try to plot the distribution, you can actually try. If you plot the distribution of the answer you get, right, it's going to be some distribution like this. Okay, and right, the more time you run, this is the number of time you get that answer. Got that answer. And this is the answer itself. Okay, that's good, right? Then the mean here is actually going to be at the correct mean by, it's called linearity of expectation. If you learn discrete math already, if you don't, then just wait for a few weeks, then you're going to learn exactly this word. The mean is guaranteed to be correct. The mean is correct. It's guaranteed to be correct. Okay, guaranteed to be the correct answer. The mean is the correct answer. Okay, but every time you try, you're gonna get some function. You're gonna get some value, right? You will never get like a billion for it because it's a very rare. You could have, it could happen, right? If you try enough time, it could happen. Okay, it could happen, but it's rare. Most likely to be around the mean. Okay, so you hope the following: the effect of the number of times that you run the simulation, right? You remember the number of points, right? The total number of points. Okay, think about this. If you pick only one time, if you do only one time, it can go everywhere, right? If you do the simulation, if you that follow for I in range, you say, okay, I'm gonna pick only one number, right? And then I'm gonna use that number as my integral, which sounds really lousy, okay? Which sounds really lousy. But then you're gonna figure out that, okay, Ajahn, wait a second, because that distribution is going to be like super wide, right? Because you can go everywhere. You can go everywhere. Okay. But as you increase the number, let's say you increase it to 10. Okay, maybe it's gonna get a little bit better. This is your now new distribution, right? We're gonna show that it actually gets narrower. Okay, but if you try this to like 100 million and whatever the number is, you try this to like a whole bunch of number, then you hope, right, that okay, your answer is going to be more and more accurate. Not more accurate. The chance that you get the right answer is more accurate, right? So for this kind of algorithm, right? For this kind of algorithm, any simulation, the statement that I'm going to say is actually true for any simulation. The thing that we are doing, right? We hope that the width of the distribution gets narrower as we put in more effort, right? With more n. Okay, we hope that it gets narrower as we add in more number of points. Okay, we're gonna prove exactly that, this fact. And this is actually a very important fact why we get away from the curse of dimensionality. And you should, if you try to do data science or whatever they call it in the next 5 years, okay, this fact is very important because there is a whole bunch of people tell you big data, use a lot of data, there is a diminishing return. There's a diminishing return. So, and the function of diminishing return is correct. Sometimes you don't need 100 million data points. You only need 1,000 to do your job correct, and then you can rerun it again. Okay. So let's do this. Okay. Let's do the analysis. Okay. So what we are interested in, right, is the width. Is the width, which is essentially the variance, right? Which is essentially the variance of the function. If you haven't taken discrete math, I'm sorry. You should take discrete math for this course. So we are trying to find the width, which is a standard deviation, or a standard deviation is variance. Okay, which is the variance of our answer, right? This is the width square, by the way. Width square. Okay. The variance of whatever we sum up, right? The sum of the sum. Okay. of the sum of m point of f of x I. Oops, let me just write the correct one. I equal 1 to m fxi yi, right? And then multiply by the area, the total area, which is fixed, right? Over m. Okay, which at least you know that I can do this, right? I can put a over m over here. Actually, let me move things a little bit, and then I'm going to put it back. Okay, at least you know enough to move a and m outside the sum. Okay, so far so good. Let me check how well you learned discrete math, because I know you didn't learn from me. Because last term my daughter was born, so I do not have time to teach you guys. Okay, let me ask you. Before that, let me ask you, do you understand why we want to calculate this? This is the width, right? We want to understand how the width grows with time. We want this width is clearly going to be some function of m, right? We want to know how the width gets narrower as a function of the number of points. This is a very important fact from this class that you should have it on your back every time you see a large data. You should think about this problem. Okay? So let me ask you, what can I do with that a over m? The variance of the constant, what can I do with it? Do you remember? The variance of, I know, 5x equals to what? Anyone? Take it out more? No, let me tell you, it's not equal to this guy. This is wrong. It's not equal to this guy, but close. Close enough that I'm going to put it there. Anyone? Wait. Anyone? Some of you, I taught discrete math to you myself. Maybe. Anyone? Okay. Let me just tell you. Let's just tell you. And then you're going to say, I saw this before. It's actually a over m squared. A over m squared. Right? When you take the constant out from the variance, you square it. At least the unit is correct, because variance has a unit of the variable inside square. Yeah. Yes, a lot of you probably took it already. You're probably the only one. You're probably the only one who haven't taken discrete math. Okay. This thing is gonna come out in like a month or so. Okay, you're gonna need to do this in a month or so. Okay, next. Okay, I think you've seen this before, that when you take out the constant from the variance, you square it. Okay, that's the fact from discrete math. Next thing is all these guys, right? The variance of the sum. And you know that you pick all these points independent of each other, right? They are all independent. What can you do with the variance of the sum though? What's so tempting to do? The variance of the sum. What's so tempting to do? What is so tempting to do? The variance of the sum is what? Anyone? The variance of the sum is, what can we do with it? The variance, oh, you probably forgot. Go back and review your discrete math. The variance of the sum is the sum of the variance. You can actually pull the sum out as well. It's the sum of the variance of f of x, I, and yi. Okay. Okay. And then we are almost done. Okay. And then the thing that you do, right? The thing that you do, how many terms are there of this guy? You add up the same number, right? The variance of the function itself. m times, right? It is going to add up to a square over m square. Let me put in the square, multiplied by m, multiplied by the variance of the f. Let me just put variance of f within the range, right? And then a whole bunch of things cancel. But the most important part here is a square variance of f over m. Okay. So you learn one very important fact, that the width square of the distribution goes down like 1 over m. Or in the other words, this is actually a true statement almost always, that the accuracy of what you are trying to measure, the sigma, the width, this is the width, right, goes down like 1 over square root m. Okay, right? Because width square, right, sigma square is goes down like 1 over m. So the width itself goes down like 1 over square root n. This is probably one of the most important facts about how to do Monte Carlo simulation. You know that if you put 100 times in more effort in, right, that this means the following. If you put in 100 times more effort, your answer is going to be only 1 over square root 100, which is 1 over 10 times more accurate. So classical, this is like much worse than what we learned before, right? We learned that at least for bisection, it goes down linear, right? Or you go down with quadratic, right? Somehow that it amplify our attempt. But for this one, you just cannot escape. For Monte Carlo simulation, it will only go down with 1 over square root n. Okay, so that's kind of limit your effort on what you want to do, right? If you put in 1,000,000 times more effort, your answer is not going to be 1,000,000 times better. It's going to be only 1,000 times better. Okay, so that's good. So this fact, if you try to do data science, remember for the rest of your life that larger data, yes, you're going to get a better answer, but the how much better goes down by a lot. Yes, sigma is a standard deviation. Okay, so that's good. This is the fact that I want you to see, that yes, you're not gonna get the same number every time, but if you do it enough time, your distribution is going to be narrow, and this is how we measure the performance of our algorithm. Okay, it's going to go down with 1 over square root n. But there is one thing that is very important that you did not see. Okay, remember when we do this, right? When we do this, we say that we try to escape the problem of the dimensionality. That is the fact that is the number of d, right? It's exponential with the number of d, right? The first time that we try to do this kind of silly thing is because the number of effort that you need to put in grows exponentially with the number of dimension. But if you just change it to like randomly pick endpoints, right? Think about this. Your performance, the performance of your algorithm, right? The accuracy, the sigma itself goes down with 1 over square root n. And let me point out, this is independent of the number of dimension. You can think it about like 0.1 in the number of dimension. But the price you pay is 1 over square root n. Okay. And the price that you pay is non-deterministic nature of this. Everyone get? So this is why when you have multiple dimension integral, you always go to Monte Carlo integral. You don't do the trapezoid method. You don't do whatever Simpson method that you did in class last time. Okay. So far so good. So I say that this very silly idea is actually very powerful. Okay, it's very powerful. Okay, any questions so far? Any questions so far? Okay, any questions so far? I think I talked enough today. Let's go back to our example. Let's go back to our example. Now you understand the algorithm that it goes down with the number of effort, but it's not going down like 1 over n squared like what we saw last time, right? In I think in trapezoid method, it goes down like 1 over n squared. That's something amplifier method. This is only 1 over square root n, not even 1 over n. Okay. So let's go back to my notebook, and I'm going to show you something more fun. Okay. So for example, we could do this as well, right? We could do something like this as well. So for example, if the region now I show you the integral of the function over a box, that's easy, right? Because it's very easy for you to generate something inside the box. Okay, it's very easy for you to generate something inside the box. Okay, but now what if you know that when you do area integral or volume integral, the limit of the volume can be any sort of shape, right? So for example, this is a sphere of radius 1, center at the origin. Okay, how do we do such a thing? Okay, how do we do such a thing? This thing is actually easy, because if you try to do this analytically, it's almost impossible if you cannot turn this into a polar coordinate and whatnot. This thing is almost impossible to do. Okay, so the way we do it is very simple, right? Okay, is to turn this into a box integral. Okay, the easiest way is to turn it into a box integral. Let me show you how. Let me show you how. Let me show you how. So for example, if we try to integrate this thing over a sphere, okay, of f of x, y, and z, dx, dy, dz, okay. So I claim that I can make this into a box integral, and this is how. When you see it, then you're gonna say that, okay, Atan, this looks so stupid, but yes, I know it works. Okay, we want to turn this into a box integral of some other function. Make sphere into voxel. No, we do something looks even more stupid, right? So we are going to turn this into a box integral that cover the whole sphere. Okay, and my function, right? Now you see, Ajahn, clearly, if I use exactly the same function, it's not going to work, right? Because the limit changes. So I need to change my function just a little bit, right? So the way I'm going to change the function is the following, okay? G of x, y, and z. Of course, it is going to look like the function itself, right? It should look like the function itself if it is inside the sphere. It is inside the sphere. Let me just copy the picture. If it is inside the sphere, copy. Yeah. But it is going to be 0 outside, right? I think given this, you kind of know, right, that it's gonna work, because all the extra area that you're integrating, right, all the extra area at the corner that you're integrating will not contribute anything to the integral at all. Okay, so far so good. So the trick that I'm showing you is how to integrate it over some other random area. Right? If you try to integrate over some random area, all you need to do is make it into a box first, and then you're done. Right? Change the function just a little bit. Okay, so far so good. So let's try exactly that. Let's do exactly that. Okay. So let me just copy this. And I'm going to do something that sounds very simple, right? We want to make sure that the box cover this. So the box that cover the sphere of radius 1 at center at the origin is exactly that box. Right? You should draw it. Make sure that it covers the whole thing. Okay. Then I just make, okay. G, X, Y, and Z. So this is, if it's inside the sphere, right? That's easy. If X squared plus Y squared plus Z squared is less than 1, this is inside. Then I'm going to return f, x, y, and z. else 0, return 0, and done. And then you just change this to G, and then you're done. There, that's all. That one good, right? If we know how to integrate the box, and then we are sort of done. Okay. This thing, I don't even know how to enter it into Wolfram Alpha. I have no idea. So that G turns that function into a box integral, and then you can do whatever the technology that you have. Are we good? Any questions so far, though? Any questions so far? Any questions so far? This thing is quite clear, right? It's actually very simple. Okay, I updated. Now, that's how you check something is inside a sphere. Right? Because if something is inside a sphere, you should be able to do this. Right? If something is inside a sphere of radius 1, then the distance between that point and the point that you choose should be less than 1. Right? If you're inside a sphere. In the homework, I think you need to move it a little bit. Yeah. Everyone got the idea, right? Okay. Now, let's go through your real gacha god. So let's think about this. Let's think about this. When I asked you earlier about how to turn, what is that? How to turn, let's say, from the random number from 0 to 1 to -1 to 1. But your real life doesn't work that way, right? Your real life doesn't work that way because if you think about it, when you play gacha game, right, it tells you, okay, what's the character on Genshin right now that people want? Can you tell me? Last time I played, it was the guy, the god at the Chinese town. I don't know his name. Shong Li, right? So for example, Shong Li, it tells you, okay, there's a 5% chance you get that. Right. Or maybe character number A, B, there is 8% chance you're gonna get that, and there's a 10% chance you're gonna get this, and there's like 2 star. Let's say this thing is like SSS, and this thing is SS and S and A class or something, and this thing is like 70% or so. Let me make sure it add up to 100. What's this? 10, 23. So this thing is 70% chance it's gonna add up. Okay. Right. So sometimes, so it's gonna look like this dice situation, right? Each number, right? Each number are going to come out at different probabilities. The question is, can we generate the dice space that has the properties? Remember the thing that we started with, right? We only have numbers from 0 to 1 uniform. This is what we have. And we want to turn this into number 1, 2, 3 to 6 with associated probability. How do we generate it though? What do you think? How would we do it though? We want to transform 0 to 1 from uniform. Oops, I should show my iPad. Sorry about that. Yeah, so we want to transform from 0 to 1 to like discrete amount of things, but each one has like different probabilities. What do you do? What do you do? Anyone has a good idea? This is like how you play your gacha. What would you do? What would you do? Expected value thing? No, we are not just trying to match the expected value. We are trying to make sure that we get number one. What's the number? 30% of the time. 0.3, probably 0.3. 2 is 0.2, and 3 is 0.1, and 4 is 0.2, 5 is 0.1, and 6 is also 0.1. So it's not expected value, right? We want to make sure that distribution we get, we're going to get 1 that many times, 2 that many times, 3 that many times. What do you think? How would we turn 0 to 1 uniform to this? Let's start with something easy. Let's start with something easy. Let's start with something. How do I make sure that I get 1 30% of the time? I only have number from 0 to 1. How do I make sure that I get add more character? I only have number from 0 to 1 uniform, but you can do anything with that number to give me 1 to 6. Anyone has a good idea? Let's see how your gacha works. Aha, very close. Very close. What do you do with 0.3? What do you do with 0.3? Anyone has a good idea though? How do you turn 0 to 1 uniform into like discrete and non-uniform? If you can turn it into discrete non-uniform, you can actually do everything. What do you think? What do you think? Okay, let's start with something easy. I want to generate 1 30% of the time and 0 70% of the time. What would you do? I want only 2 numbers, 0 or 1, but I don't want it to be 50-50. I want it to be 30% and 70%. Anyone? Help me on this one. I want you to think along though. I want you to think along. The answer sound really silly, but let me know. 0 to 1 times 0.7. It's not going to work, right? If you times 0.7, right? You generate from 0 to 1, then it's not, it doesn't even return the right thing, right? So if you get 0.5, then you multiply by 0.7, and then you get 0.35, then what? This is not what we want, right? I want 0 or 1. Okay? So let me tell you something extremely stupid. You just say, okay, I get random, right? Random number. I know that this thing is from 0 to 1. All I need to do that if x is less than 0.3, I'm going to return 1. Else, I'm going to return 0. Aha, right? You see that it's going to work right away. That 30% of the time, you're going to be in this time. And whatever the rest, 70% is going to be in that range. Okay, so that's good. Now, how about if I want, how about let's go back to 1 to 6. What would you do? What would you do? If I want 1 to 6 with exactly that probability. Anyone? 1 to 6 with exactly that probabilities. So when should you return 1? Can you tell me? When should you return 1? So x is random from 0 to 1, uniform. When should I return 1? Given x, when should I return 1? I want to make sure that I return 1 30% of the time. When should I return 1? Return 1. Are you guys still here? Good, right. All you need to do, right? If less than 0.3, right? Then we are going to return 1, right? And then you want to make sure that, okay, this thing is gone to number 1. You want to make sure that the other 20% goes to number 2. So you do else if, right? X less than 0.5 to make sure that, because this thing is 0.3 already, you want another 0.2. So this is going to be 0.5. Right? So you calculate something like the cumulative distribution function. So this thing is going to give you 2, else if x is less than 0.6, give you 3, and so on. Okay, so that's good. Let's write exactly that, and then we're going to use this to do something really cool that you have no idea how to calculate before. Everyone understand the problem, right? So let's do this. Yeah, guys, let's call it gacha better. Exactly, this is exactly what gacha simulator does. So that's why I call the function gacha. They calculate something called the sum that you have is called cumulative distribution function. Okay, if so x is np.random, right? This thing is from 0 to 1. If x is less than 0.3, return 1. They probably write a better code. Else if x is less than 0.5, return 2. Else if x is less than 0.6, right? Return 3. Else if x is less than 0.7, return 4. Else if this looks like programming 1, right? When you write this many else, you can actually write this in a couple lines. I'm too lazy today. Oh, return number 4 is actually not that. It's 0.8, right? And 0.9, return 5, else, return 6. That's it. That's your gacha code. Okay, and then you can say, okay, gacha, okay, what we got. So this is like, what should we call it? Let's call it the dices. Okay, so we can call gacha many times, right? 100 times. I in range 1,000, and then we can plot the histogram. plt.hist dices, and okay, let me make it more bins. Bin is 50. Okay, that's better, right? So this thing close enough to 300, right? It doesn't have to be exactly 300. This is 200, 200, 100, 100, 100, close enough to what we get. So far so good, right? Now we have our gacha god over here. Okay, function called gacha, which gives you the exact distribution that you need. Okay, how about the expected value? How about the expected value? What is the expected value of this guy? Do you know how to calculate it? What would you do? What would you do? What would you do? What would you do? Expected value? How would you do it? How would you do it? Okay. If you learn discrete math and then you do it well, you know that you should multiply this number by that number, this number by that number, and so on, and add them up, right? But you can do something a lot better. So for example, the expected value by the definition is the mean, right? So I just do this. np.mean of the dices that I throw, and then okay, that's close enough, right? Okay, and you know that the more gacha I throw, the better my answer is. Are we good? Right? So the goal here, I want you to see that this is a simulation, right? You can simulate the gacha game how many times you want, and you can calculate the expected value. Okay. Now, let's look at the next one. What if you throw two dice, A and B? What if you throw two dice, A and B? And what is the expected value? Right? Then that thing is also very easy, right? So you throw every time, then you do the gacha every time, right? So you gacha plus gacha in range. I don't know, 1,000, 10,000, right? So the list here is going to contain the outcome of each experiment. Oops. Wait, why is it true? Did I forget to return? No. Oh, maybe different. Wait, why is it true? Oh, yeah. So this is the outcome of each of the term, right? So if you want to find the expected value, that's easy, right? And if you learn something about linearity or expectation, it should be 2 times that number. Okay, are we good? Any questions so far? Or any questions so far? You guys are really quiet. I'm not sure if I lost you already or not. Okay, any questions so far? Okay, you are just enjoying. Good for you. Now, how about, you know that number 2 and number 3, right? You know how to calculate by hands. If you have enough time, you can calculate by hands. Multiply this by that, this by that. Now let's start with something you don't want to calculate by hand. You could though, but you don't want to. What if I throw 2 dice, but instead of adding, I multiply the 2 dice? And I want to know the mean. I want to know the mean. What would you do though? What would you do? What would you do? You just throw the dice 2 times, right? That's all. You just throw the dice 2 times. Ah, now I get all the faces. And if I wanted the expected rate, okay, that's also easy. Right? That one is also easy. If I want the probability, that's also easy. POT.his. Right? Then most of the time you're gonna get this. Sometimes you're gonna get this. There's some number that you never get. Let me make sure that bins is 100. Okay. This is the probability that you're gonna get each of the number. Right? There are some number that's rare. So for example, number 5 over here. 5 is probably that it's a prime, so it should be small, right? So for example, a number like 6 or 4, there are more than one way to get it, so the probability is higher. Okay, and you know there's no way for you to get 35, right? Because you don't have 7 and 5. Okay, so you know that by just this very simple 3 lines of code, you get the probability distribution of whatever you're gonna get. Okay, so far so good. So I think this thing is quite clear to you. It's simple, right? You just get the computer to play the games and then you count all the results. Now, let's do something a little bit harder. Okay, let's do something a little bit harder. What if we play the game of two dice, right? Of two dice, okay? There's a you and your friend, and then each turn you throw two dice, you take the product, whoever gets the more number win, and then I ask you, what is the probability of getting a draw? That is clear something you don't want to calculate by hands because there are so many cases that you need to take into account. So what would you do though? What would you do to get this number to me? Can you give me this number? Anyone? What's the idea? What's the idea? What's the idea? What's the idea? Right. Right. Just that. You just get people to play the game, right? Just get people to play the game. And then you want to know how many times it returns true. Right. So dices going to be a whole bunch of array of true and false. Then all you need to do, right? You want to know the probability. Just count how many times you get true over the length, right? Which you can do that by np.sum because Python treat true as one. Divide by 10,000. Done. 20%. You get a draw. No need to calculate everything. Okay. So how about this? I think everyone gets the idea, right? The goal is just to generate enough sample that you want. How about something a little bit harder? The same game. But your first dice is 3. You want to know what's the chance of you winning, right? Same game. You throw 2 dice. Your first dice is 3. Wait. This is not, no, this is not correct, right? It's gacha, because you want to throw the dice twice. Okay, that's better. 8% of drawing. Sorry about that. Right, you throw the dice twice and you add. So this is whatever the first guy get. This is whatever the second guy get. Okay. Now, how about number 7? Can you calculate the probability of you winning? I copied this because you only need to change like 3 characters. What would you do? What would you do? What would you put here? This is more important. Very good. Right. Of you winning, so you just need to make sure that okay, you are the first guy, right? And you get 3 already, and then you throw another dice, and then wait for the other guy to throw the other 2 dice, and then you just calculate probability. Oh, if your first dice is 3, you know you have 50%, 55% chance of winning. As simple as that. Okay? This technique is so powerful. You don't want to calculate everything analytically all the times. Okay. Let me make sure one thing though. Sorry about that. Let me check one thing. Check one thing. If I left this, 2 seconds. Okay, good. Any questions for today though? Any questions for today? Any questions for today? Let me go back here. Right. Let me skip this for today. We're gonna do this next time. We can actually answer a whole bunch of things about the stock. Okay, given the exact idea that you play gacha game, the exact idea, you can answer a whole bunch of things about stock. Okay, as long as, so the idea is you generate a whole bunch of stocks and then you see which one falls. Okay, any questions for today though? Any questions for today? So today is pretty light, I think. So if no question, we are going to call it a day, and let me remind you about the midterm. Midterm is going to be posted early next week. Once I post it, I'll announce it on the Discord and the Canvas. Okay, midterm. Don't forget. It's not that hard though. There's going to be a section that I want to make sure you pass. And there's a section that I want to make sure that you some creative one. Okay. Any questions or any question? If not, we're gonna call it a day and do something else. Okay. We're gonna do the stock next time. We're gonna do the stock next time. Okay. If not, let's call it a day and see you next week. Next week we have class though. Bye everyone.